Okay, couple of things. I had sent a link to a GitHub repository, which is the set of programs for computing Lyapunov exponents and Lyapunov vectors. And those are illustrated for two different systems, Lorentz 63 and Lorentz 96. Wait, did you get an email? Wait, you have not received the email. Okay, so that I had sent him yesterday, and wow, okay, fine. So then, just give me 1 second. So, okay, this is one of at least this is visible, right? It's a tiny URL, so hopefully it's easy to copy. All no caps, all small letters, and let me create a tiny URL for this for the other one as well. So I will write that on the board. Okay, so that's the other one. The first one is a notebook that I think most of you should have some familiarity with. It's just Lorentz 63 system, solving it with using standard packages and so on and so forth. But there is an exercise at the top of it. And that's what I would like to focus on for part of the talk at least. And the second one is, so this is simply for the Lorentz 63, and this is for computing the Lyapunov vectors. Computation. Yeah. So let's see how far we get to this part and so on, because this needs installation of JAX, unfortunately. But no, I mean, not unfortunately, it makes it faster. But okay, so let's start there. I will start maybe with couple of things about some theory behind this, and then we can switch to looking actually at going through this notebook and see what happens. Yeah. Okay, so first exercise was for this Lorentz system. The idea is as follows. Any of the numerical methods essentially give you approximation of these systems. So we have, so the problem is as follows. We have this equation x dot equal to f of x, and the numerical solution, so the ODE is this, and the numerical solution essentially gives you approximation at different times. So tk, x of tk, x tilde, let me call it. So 0 to n, and let's say equal to k times h. So this is supposed to approximate the true solution to the differential equation, right? So if I take a certain time grid, start at time 0, let's say time t1, time t2, or let me just call it like this, t 2t, 3t, some k, n, t, and so on and so forth, and try to compare the true solution. So the true solution, of course, is continuous in time, and I can look at the value of the or the solution at different time points. That's a true solution, and compare it with the numerical approximation. So the approximate solution, and the approximate solution will be available only at finitely many time instances. So I'll just show it by dots like this. So here is another approximate solution, another one more, and so on and so forth. Right? And in between, we can't do anything. So maybe we can just do something like, okay, so firstly, if t is not equal to h, so this is the step size of this numerical solver. So we are taking time steps of size h and going forward in time. And so I could essentially actually have a solution. So there could be h, 2h, and so on in between. So I will have a solution at times in between as well, such that eventually I get to the time t, 2t, and so on, right? And there are multiple ways to think about this. If you want to think of this as a continuous time solution, one way is simply join them by straight lines. So linear interpolation between the time instances at which we are doing the computation is one way to think of it as a continuous time solution, right? But so anyway, but that's not necessary right now for us. So how do we check how good of a numerical approximation do we have in the first place? And I'm kind of emphasizing this for a couple of reasons I'll come to in a minute. Maybe you have seen this in your courses before, maybe not, I don't know. So let's just be clear about this. So if I want to compare, one way to think about understanding how good of a solution I have is to say that, okay, if I knew x, let's call it x true, at the time, say, k t, minus the x approximate that we have, for example, using some numerical scheme like that, at the same time, kt, and something like a norm of this solution. So we could take, say, the L2 norm, squares of all the components of these differences, and possibly something like, let's say, the sum of k goes from 1 to n, or some such metric for checking how close we are to the solution we are trying to approximate. The problem is we cannot do this because this is unknown. So given a solution, given a numerical solution, how do we check, oh, is this reasonable? Is it good enough approximation? What's one of the standard ways that numerical methods you kind of test or you check the accuracy of numerical methods? One way to do this is a systematic way to increase the accuracy is typically decrease the step size. If the step size goes down, you expect the quality of the approximation or the accuracy of this approximation to go up. And you expect this solution, the approximate one, to be closer to the true one if the step size in between were taken to be smaller. So let's see whether that happens or not. So how do we check that? Well, so if this is unknown, so we can't do this. So one placeholder for this would be to see whether you can. So let me put the step size over here. So I guess the step size is, say, h, right? But we could, this quantity we cannot compute because we don't know this. What we can compute actually is x approximate with a step size, let's say h over 2. You decrease the step size by, say, half, kt minus s approximate h kt, and now do the same check, and maybe sum n goes from k goes from 1 to n. And now this quantity is explicitly computable. We can actually compute this quantity. We could do this multiple times. For example, reduce the step size by say h over 4, h over the standard numerical. If these are methods like say Runge-Kutta, Euler method, this and that and so on, actually Euler is a bit complicated, but anyway, forget Euler. RK4, for example, there is theoretical results that say that if you decrease the step size as h goes to 0, this quantity will actually go to 0, theoretically. That is, as the step size becomes smaller and smaller, we get a better and better approximation, or rather, the correct thing to say is that this is actually, as h decreases, this is essentially a Cauchy sequence. But because Cauchy sequence in this case would be convergent, there is a limit, and the limit actually will be the true solution we want. If that argument you didn't fully follow, it's perfectly okay, don't worry about it. Essentially what it means is that as h goes to 0, the solution that you will get will be a good approximation of the true solution. Is what the mathematical statement I made about half a minute ago exactly means. Okay, but anyway, so at least does this happen? And should we try to do that? You have the notebook here. If you have your own RK4 solver for Lawrence 6316, please use it. This is just one. This notebook I have uploaded. It's just one example. I just coded up and so on. But if you have your own solver that you are using in the past, that's okay. So the idea is as follows. Let's call this quantity, let's say the error with a step size h. Right? So you're taking a step size h, you do the same computation, but with step size h over 2. So now to go from 0 to t, and to be precise, let's fix some numbers. What kind of exercise do we want to do? Let's say that t is equal to 0. Say, I don't know, 0.1. And let's start with little h of 0.01. So essentially we'll take 10 steps to go up to 0.1, 10 more steps to go up to 0.2, and so on and so forth. And let's say nt is equal to 1. So there will be a total of 10. I'm not sure why I'm using 10 everywhere, but anyway, whatever. So you go up to time 1. Actually, time 1 may not be, so first thing we could try with time 1, but to be more ambitious, it could be that you go for slightly longer time, let's say something like 5. Yeah? And now we can compute this quantity explicitly with a step size, let's say h. Then we could try to do this with a step size e of h over 2. What will that mean? We compute the solution with step size h over 2 and the solution with step size h over 4. And then that will be the error with those two. Or we could then compute h over 4. So h over 4 and h over 8 and so on. What is it that is expected? What is expected is that as the step size becomes smaller and smaller, these errors should become smaller and smaller. That is, E of h should be large, or E of h by 2 should be smaller than that, this should be smaller than that, and so on and so forth. Have you tried this before? How many of you have actually tried to implement? This is what the theory says. What I just said in words is what the theory implies. In fact, the theory actually gives you the rate at which this function will go to 0 as a function of h. RK4, in the case of RK4, this will go to 0 as h to the power 4 with multiplied by some constant. And h to the power 4 as h goes to 0 goes to 0, but then there is a constant multiplying it. Does this happen or does this not happen? I guess that's the question. Actually, there are multiple ways to formulate this question, by the way. You don't need to take the sum of these discrepancies at different times. You could simply take, for example, you could define the error to be something like, let's say, e tilde of h is just the solution at time nt, the final. So this is just the final step error, not the sum of errors over a certain time interval. Minus x h and t, whatever the final time. So I could call this t final or something like that, and you just take this. Yes. Yes. Yeah. So yeah. So these values will be different for different systems. I mean, yeah. So we will come to that point. What do you mean by trajectory will diverge? Exactly. So I completely agree with you. I totally agree with you. Yes. So that is a possibility. Does that happen or does that not happen? Have you tried it? There is theory and then there is practice. Uh, and actually, there is the theory of the practice as well. But anyway, here is a simple exercise. Okay. So uh, if it's some nice smooth function, choose whatever you want, sine of x, cosine of x, choose the value of x, that's your favorite pi or e or whatever it is. Some nice smooth function f of x to be some nice value that you choose, doesn't matter, no singularities, no complicated stuff. This is the finite difference derivative of a function f of x plus h minus f of x divided by h. And as h goes to 0, you would expect this quantity to go to 0. F prime is just the known, so take a known function so that you know what this quantity is. And let's say f of x is x square at x equal to 1. This will be 2x, that is 2 times 1, just 2, minus x plus h square minus x square divided by h. What does this look like as a function of h? E of h as a function of h. Taylor series expansion. If you don't know this, that's perfectly okay. As long as you know Taylor series, you will be able to get the answer, hopefully within 2 minutes, 5 minutes. Expand, just expand this in Taylor series. Sorry, expand this, f of x plus h in Taylor series. What does this look like for h and h, say, call it small. So small values of, so start with h equal to say 0.05, 0.01, or maybe 10 to the power minus 3. And so h, let's say if this, the highest value of h that you are considering is say 10 to minus 3. For h less than 10 to minus 3, what does this function look like? Wait, no, please, don't look at the board. Look at your notebook. Finish the calculation of expanding this in Taylor series. And I basically want the smallest order term in h that remains for this function. So that's one exercise. And then we'll come back to the question that you asked about chaotic systems and so on and so forth. Sure. Maybe we first make a guess. But I guess if you have never done this competition before, then maybe making a guess, I don't know. But I mean, this should have been done somewhere in your curriculum. Maybe 12th standard or something like that, right? Possibly, but I don't know. Uh, so, okay, so somebody should make a guess in the next 2 minutes. Sorry? Oh, what was the hint, Neelima?
Power of it.
It's a power of H. Yes. Oh, if you have if you have done a numerical analysis course, try to remember what is called the order of convergence of a method. It will look like U-shaped curve. Okay. So somebody says it's U-shaped. Can you be more precise in terms of what you mean by U-shaped? Sorry? Hyperbola. Okay, so what are the asymptotes of the hyperbola? If it's a hyperbola, x-axis and y-axis, no, they're not. There is a minimum. Why? So why is there a minimum? The answer is correct. It's not a parabola. The topological shape is correct, but not the details. This side, what's okay? So the shape is roughly correct. What's this side of this curve? No, I don't want to go to high values of. So forget the high values. Just small enough values. 10 to minus 3, 10 to minus 2, some. Sorry? So what's, some of you did this competition, no, at least. What's the lowest order term that you get? One? I mean, no. Is it h, h square, h cube? What remains? H. So the linear term in h remains. Sorry? You need to speak up or please come in the front. I'm not sure why you're so far from me, but anyway, that's okay. But at least then speak up. Yeah, that's okay. But please, that won't last for too long. Once we start doing the notebook, I'm going to start walking around. So I'll be closer to you, then, then you won't feel safe. Okay. But please speak up. I couldn't hear you. Okay, so but at least the lowest order term, of course, h goes to 0, this will go to 0. That I agree with. So so the theoretical answer, so here is the answer. So h goes to, as h goes to 0, this goes to 0 is what he just convinced us. If you're not convinced of his argument, please ask him to convince you. And how does it go to 0? You said that there is a linear term in h, which means it goes to 0 as a straight line, right? That's how h goes to 0. I mean, as h goes to 0, this is what happens. Somebody else said there that, sorry, I don't know your names. I should be better at this, but anyway, that it looks like a parabola. Okay, it's not exactly a parabola because we know theoretically that this is what it should look like. So that actually does happen. But as h becomes smaller and smaller and smaller, in fact, it does not go to 0. Okay, what's this part of it? In fact, let me be more, yeah, okay. I guess I should just put it like this and then ask, what is this part here? What is this function? What is the functional? So this is linear in h, right? So this is something like ch, this part of the curve. What is this part of the curve? It's not exponential. Inverse, sorry? Impulse function? No, impulse function is it's discontinuous. There's no discontinuity here. 1 by h, okay. Any other guesses? Okay, so it is in fact, let's say this is C1 by h, this is C2 by h. Why is this C2 by h? Was that a guess or did you know the theory behind why it is 1 by h? Okay, so it is in fact 1 by h, but it's 1 by h because of numerical accuracy. That is because of rounding errors. And I'm not going to go to the theory of rounding. Why the rounding errors in computation of this quantity give you a 1 by h always. So it's a nice exercise to work out. And in particular, it's a nice numerical exercise to do. Do these plots. In fact, do these plots in semi-log plot, for example. It's better. Semi-log plots will show you the slopes, -1 and 1. Right? So instead of doing this, do a semi-log plot of this. And then, if you're convinced that you understand what happened, do the following exercise. Replace this bit of it by higher order approximation. For example, replace it by f of x plus h minus f of x minus h over 2h, for example. And then, you know better ways to compute derivatives, use those if you want, and so on and so forth. What will happen for this case? It's not, so which part will change, which part will not change, or nothing will change? I don't know. I'll leave it to you to decide. Or just do it. Now that you have computers in front of you, just do it. Don't even think about it. Anyway, okay. So actually, no, sorry. Think about it, but also do it. Sorry. The reason I brought this up was when you said that E of h is supposed to go to 0. But it may not because of chaotic nature. Can we understand what happens to E of h based both on the theory of the numerical approximations, and what chaos will do to these errors? Yeah. So that's partly the exercise in this notebook over here. Okay. This was just a complete aside about just being careful with numerics in general. Okay. Do we? I haven't. Well, not quite yet. It's. I guess the theme has always been the behavior of uncertainties, and this is essentially what relates to how uncertainties change. Right? These errors. As I said, I don't like the term error too much, but again, in this case, actually, it is error. But if you were to now think of this approximate solution as approximation because of some uncertainty in the system, then how does this behave? How do these approximate solutions behave in time? Okay, that's one exercise that we should do. And the other one would be understanding this Lyapunov exponents and Lyapunov vectors, right? So let me try to finish defining the Lyapunov exponents, Lyapunov vectors in a minute, but actually maybe I'll jump a bit and say what happens to uncertainties. Completely different topic. Have you studied at least basic probability theory in the sense of actually for now just normal or Gaussian random variable? How many of you know how to write down the density of a Gaussian or a normal random variable? So for example, if I say x is a normal random variable with mean 0 and variance 1, do you know how to write down the probability density of x? Have you seen this before? Yes? If you don't remember, that's okay. Do you know what, at some point, you have seen this in your life, that you know what this is supposed to be? At least the picture, hopefully, that looks like this. And this is 0. Actually, let me just say m and sigma square. This will be m, and this will be some measure of sigma. At some point, it will be equal to sigma, but anyway. Yeah. And that's one dimensional. How about higher dimensions? Yes, no, like any, if I, so this is basically a random variable. Oh, normal, or Gaussian. So
Yeah.
m is the mean, and this is the variance. So normal or Gaussian random variable in one dimension. Right? In order to go to higher dimensions, because we were talking about systems of differential equations in, let's say, Rn, Lorentz system is in R3, three-dimensional. So we will have to talk about higher dimensional random variables, and I'll for now just stick to Gaussian random variables. So if x is again a normal, so this n is for normal or Gaussian, is in say R2. Okay, let me just write it for Rn for now, and n equal to 2 will be a Gaussian random variable in R2. We need to specify the mean. The mean of a random variable, of course, will have the same dimension as this object, m, and the variance will get replaced by the variances and the covariances of the different components of these random variables. So there will be so this is a n-dimensional vector and sigma, which is a n cross n matrix. Symmetric, positive, definite. So this is what is called a covariance. Okay. What covariance is? Okay, here is a simple illustration or two-dimensional kind of illustration where this is the probability density function of a single Gaussian normal random variable. Yeah. So how many of you have not at all studied probability theory? If that is the case, please let me know, and then maybe I'll explain a bit more about. Okay, so at least in principle you have seen some of this before. In high, so in 2 dimensions, for example, so if I have, let's say, two random variables x1 and x2, and I want to understand what's the behavior of a random variable, one way to think about this is to look at the plot of the probability density of this function. The probability density will tell you how certain or uncertain these quantities can be, right? And the probability density for, let's say, this two-dimensional Gaussian random variable. Of course, that's a function. So I have to draw, in principle, what I should be drawing is a function like this, that P of x1, x2 as a function of x1 and x2. So some surface like this. I can't draw surfaces on the blackboard. And so what we will do is look at the surface from the top. Look at constant, the contours of constant values of that function. So take a surface, cut it at a certain value, and what you get is a curve. Cut it at a different value, you get a different curve. You cut it at a different value, you get a third curve, and so on and so forth. And that gives you some idea about what this function looks like. What this, in this case, now probability density of the Gaussian random variable will look like. And here is the result without proving it or anything. I'm just going to state the fact is as follows, that it will be peaked at the mean m. So m has two components, m1 and m2. So this is m1, m2. The peak will be at m1, the mean m, and the constant, the contours of constant probability density p of x are ellipses of this. So these should be ellipses, but this time they don't look exactly like ellipses, but anyway, symmetric, nice, beautiful ellipses and so on. So of course each ellipse has a, actually all of them should have identical semi-major and semi-minor axes. These axes, those are defined by eigenvectors of the covariance matrix. So these are eigenvectors of sigma are these, and the means are different. So that's why m1 and m2. So I put the components. So m, I'm writing as a vector m1 comma m2, the two means. They will be different as well. They need not be the same. They could be different. Yes, yes. Yeah.
What?
So
sigma 1 squared, sigma 2 squared, or if you like.
No, actually more than that, because covariance, in fact, is a matrix. So in this case, n cross n, so 2 cross 2 matrix, which will be sigma 1 square, sigma 2 square, the standard deviation, the variances, the squares of standard deviations of the first and the second component, and the correlations. So a standard way of writing this matrix is the following. This is what is called correlation. Oh, sorry. Yes. So I guess I was taking this as the stopping line, but actually the stopping line should maybe here. But yeah, okay, fine. I will. Sorry. So this is what the rho is called correlation. Rho is the correlation, and that's a standard way. Again, definition of correlation. Actually, this follows from the definition of correlation. But anyway, this form, the way I wrote the matrix follows from the definition of what is called correlation. But anyway, and so the way I drew it, rho is actually positive. So this is the specific case when rho is positive. This picture is for rho positive. If rho is negative, these ellipses with these elongated ellipses would have been tilted the other way. And why is that the case and so on? That's a slightly long, it's a longish calculation. Actually, maybe half a blackboard or something, but still, anyway. So, okay, so in general, a higher dimensional Gaussian random variable has two important quantities associated to it. One is the mean, and the other is the covariance. The covariance consists of multiple things. One is just the variances or uncertainties in individual directions. Sigma 1, sigma 2 are the standard deviations of x1 and x2. And how does the uncertainty in one random variable x1 relate to the uncertainty in the other random variable x2, which is given by the correlation? The off-diagonal terms of the covariance matrix give you the relation between uncertainty of one and the other. And of course, for an n cross n matrix, there will be n standard deviations along the diagonal, and the upper diagonal, it's symmetric matrix, so only the upper diagonal part will have the correlations between the different random variables and so on. Yeah. Okay, so should look, okay, let me keep it. If we were talking about evolution, time evolution of uncertainties in a dynamical system. How will that happen? I want to keep this. Okay, you guys, yeah, at least some of you have hopefully noted this down, and we'll use that as a reference. So I can erase this for now, because this is what we'll do with the notebook that we have currently. And then, okay, how does uncertainty evolve in time? So this is so forget the linear OD. Consider the nonlinear OD. Consider AX, which is a linear autonomous ODE. And suppose I assume that, so if x naught, the initial condition, is uncertain, so usually what we think about is, oh, I give you an initial condition, you give me a solution. So think of for a given initial condition, you find x of t, which is a solution. In this case, in fact, it's explicit, e to the power at times x naught, and that's an analytical solution. But if x naught is actually a random variable, that is, suppose I give you that it has a Gaussian or normal density with a mean m naught and a covariance sigma naught, then what is x of t? If x naught is uncertain, x of t is also going to be uncertain. And how do we specify uncertain quantities? In terms of random variables or in terms of the probability densities of those random variables. So x naught at time t equal to 0 is a random, is normal and Gaussian. X of t at some time t, at later time t, will be a also actually will also be a random variable. And by question mark, I mean what is the probability density of x as a function of time? If x naught is specified, the solution is a linear function of x naught. Since the solution is a linear function of x naught, so here, let me, maybe it's worth writing it down. Linear function of initial condition for the linear system. And a second fact, which I'm not going to prove in any way, a linear transformation or a linear function of a Gaussian I will keep using the term Gaussian random variable or a normal random variable interchangeably. Same thing, no difference whatsoever. That means that it has a covariance, it has a probability density given by the mean and a covariance matrix. I haven't written down the covariance density for a n-dimensional random variable, but we can, if needed, we'll do that in a minute. So a linear function of a Gaussian random variable is also Gaussian. Okay. So the first fact tells us, sorry, the first fact is specific to solutions to linear differential equations. The second fact is a general fact about Gaussian random variables. You write down a linear transformation of a Gaussian random variable, it is also Gaussian. So let's say if x is in Rn and y is equal to mx plus c and is in Rk, is if x is Gaussian, y is just a linear function of x, then y is also Gaussian, and the mean and the covariance are as follows. Oh, sorry, there are too many m's. That's a mean, so let me make this a different matrix, I don't know, B. It is Bm plus C, comma, so that's a covariance matrix and that's a mean of that random variable y. And that's fact, so that this is, so to say, the mathematically precise version of this statement here. Yeah? So now we can combine these two facts. The solutions of a differential equation are linear functions of the initial condition. If I give you the initial condition to be a Gaussian random variable, then because of this second fact, the solution at a time t is a random variable, which is also going to be Gaussian with some mean. Of course, that will depend on time. So I will write it as m of t, and some covariance that will also depend on time. So the mean and the covariance of these random variable will now evolve as a function of time. And basically that, so because x naught is uncertain, x of t is uncertain, the uncertainty in x naught is largely captured by the variances and the covariances or the correlations of which are terms of which are the elements of the matrix sigma naught. Those evolve in time, and those are captured by the time evolution of the covariance of this quantity x of t, right? So the time evolution of the covariance of the solutions to the differential equation capture the time evolution of the uncertainties. Without proving absolutely, I didn't prove this either. This is actually part of a probability theory course. Similar to that, I will simply state here is part of the motivation of what I'm about to state. Sigma of t is going to be a function of sigma naught in some way, right? The covariance at some later time will depend on sigma naught. These are some nice smooth systems. In fact, these are quantities which are functions of time. They happen to be smooth functions of time. And going along the same direction, since we wrote down the differential equation for the quantity x itself, correspondingly, there are differential equations for quantity m and sigma. Right? You know what x of t as a function of x naught looks like. It's e to the power at times x naught. We know what a linear transformation does to the covariance. You pre-multiply by the matrix and post-multiply by its transpose. And so when you take the differential equation for this, so essentially what I just said in words combined into, so because x of t is equal to e to the power at x naught, this will give us essentially that sigma of t is e to the power at x naught times e to the power at transpose. This fact here. But we can differentiate this and get a differential equation, and the differential equation or sigma dot is equal to a sigma plus sigma 8 transpose. I'll leave it as exercise. Differentiate that and see what you get. Right? You have to differentiate this, so differentiate the first term. It's a chain rule. That will give you the first part, then differentiate the second term, that will give you the second term, and that's it. It's a straightforward exercise, essentially. In matrix differentiation, that's all. Okay, so the way the uncertainties, that is the covariance matrix of a differential equation evolves is by a differential equation that contains, that looks almost identical to what the differential equation, original differential equation looked like, except now for matrix, sigma, with additional term that is sigma A transpose. So that's a bit of a complication, if you wish, but kind of similar to the linear differential equation that we originally started with. What happens for hop, skip, and jump? Now there is a big jump. All of this was for the linear system. For a non-linear differential equation, that's where the big jump will happen now. Because none of this theory is going to apply for the non-linear differential equation. The solution of a non-linear differential equation is not going to be a linear function of the initial condition. So this fact is not going to be extremely terribly useful to prove anything much about the nonlinear system. But, and this is the jump where I will simply state a fact that the covariance of, so so now, so all the green was kind of interlude, going back to thinking about what the nonlinear differential equation does, and let's say x naught is random. Right? So we have a differential equation. We do not know exactly the initial condition. Since the initial condition is uncertain, we think of this as a random variable. It will have its own probability density. Corresponding to the probability density, there is a covariance. Because the initial condition is random, the solution at time t will be also a random variable. it will have its own covariance. And the covariance let's call it sigma of t of x of t is given by the following. Sigma dot, almost like this. It's actually exactly like this, except that now what is the role of what's A? Of course, it's not a linear differential equation anymore. But this is where we go back to thinking about what we did yesterday, towards the very end of yesterday's lecture. The time evolution of the uncertainties or perturbations is given by the Jacobian, and the same way the covariance also now evolves by f of x times sigma plus sigma plus times f of x transpose. So understanding the behavior of the solutions of the linearized equation only, so if you look at only this bit of it, essentially, this is kind of like, this is exactly how the linear equation looks like, right? So to understand the time evolution of the uncertainties of a dynamical system, either the linear or the non-linear, and I'm thinking of capturing the evolution of uncertainties in terms of the covariance of these random variables, is very closely related to understanding the time evolution of, and hence we need to study. Okay, hence, okay, this is one of the reasons. I mean, to do this, we need to study, we need to understand the time behavior of equations of the form m dot equal to f of x times m, which is what I wrote down yesterday. The linearization of the nonlinear differential equation. Linearization is a term that's used for basically this. This is called a linearization of the nonlinear differential equation, right? Okay, so time evolution of this is very closely related to that, and so the time evolution of this matrix M, of course, it's so I guess I will now state a few things. Let's motivate and then state a few things. Suppose let's go back to this this system over here. I will erase this for now. If you still need the reference later, I can. Hopefully, some of you have copied this because actually I don't think I saved it. If I have closed my tab, then I have lost this tiny URL. But okay, so let's consider this case: x dot equal to 1, 0, 0, minus 1, x. As simple a high dimensional system as it can get. Maybe you can think of something simpler, but anyway, what does the solution to this do? First component is e to the power t times x naught. The second component is e to the power minus t x naught. The first component grows. The second component decays. And okay, this is also called a saddle. What happens to that? What happens to this equation here? I mean, this equation exactly actually does what this equation does for two different initial conditions. So m dot equal to 1, 0, 0, minus 1, m. And I guess I didn't write down the initial condition. M of 0 equal to, say, identity will simply give you that m of t is equal to e to the power t 0, 0, e to the power minus t. So this will be the growing direction, and this will be the decaying direction. The first one, the second direction, the second eigenvector, E2, will be the decaying one in this case, right? This will be the positive Lyapunov exponent 1, and this will be the negative Lyapunov exponent. In fact, in this case, just minus 1. Yeah, for this linear system. I haven't defined Lyapunov exponent. Sorry, they will come. The definition will follow at some point, but it's basically how fast exponentially things grow or decay. Now this, so there are basically the eigenvectors or eigenvalues of, as I said, in the case of non-autonomous linear system, the eigenvalues and eigenvectors determine these directions, stability or instability directions. That's not quite the case for the non-autonomous system. But we still want to understand if there are growing and decaying directions for a system of this type or not. In general, what will happen is that there will be components of M that will grow exponentially. There will be components of M that will decay exponentially fast. So M of t becomes ill-conditioned very quickly. So I guess I haven't specified ill-conditioned. Essentially, what this means is you have very large and very small components of this matrix, and that matrix becomes ill-conditioned. Or for example, the ratio of, let's say, the highest and the lowest eigenvalue becomes very large, and so on and so multiple ways to define ill-conditioning. But effectively, what this leads to is loss of numerical accuracy in time evolving this kind of system. Because the matrix becomes ill-conditioned, eventually it just becomes completely useless to time evolve it forward in time. And
yeah. Give some idea of the RAM.
Oof. Well, actually both memory and computation. If this is n, then that's n square. So square. So if there are a million equations here, like in climate, that's million times million equations. Nobody has ever solved them. So for climate, you never do this in the first place. For climate, we never do this. This is impossible to do. This is impossible to do for weather models. This is impossible to do for climate models. And that's why we need then approximation methods to compute things that are of relevance associated to this. In particular, the eigenvectors and eigenvalues of some of the, we can't compute all the eigenvectors and eigenvalues of interest. Sorry, we cannot compute all the eigenvalues or eigenvectors because we cannot even compute this whole matrix. It's a million cross million matrix evolving in time. That's impossible. Maybe we can only compute a finitely many eigenvalues, eigenvectors, which is what is actually done in practice. So, and that's where understanding, so if we could actually solve this and get all the eigenvectors, eigenvalues, and so on, then in principle, that's fine, but that's essentially impossible to do. So the algorithms, so the method to compute some of these eigenvalues or eigenvectors is, I guess, wait, what time did I start? What time am I supposed to? I'm supposed to stop in 10 minutes. Yeah. I thought, because I thought I had more lectures, I maybe planned a bit too many things, and then now I'm running out of time, even after having more talks than I thought I will. But sorry. 5 minutes?
Today's talk at the 10:40.
Which is right now.
Right.
Let's stop. Okay, no, let me wrap up and sort of say put it all together into one place, and then yeah, sorry, and I'll make the announcement. Yes, yeah. Now I think the audience has stabilized. So there is a swap of talks. Rupali will give both the talks in the afternoon. And wait, sorry, who is talking? You're talking. Sorry, you told me. I completely forgot. So Ambika will talk right now at 11:20. Rupali will give 2 talks in the afternoon, and I guess Nitin's remains to the last talk. And okay, sorry. So post tea in the. Sorry, I forgot it in this. Okay, so. And so that's one change. And let me just wrap up where one thing we could have done. We didn't actually we didn't actually run any of these. So this I will leave as an exercise too. This errors, growth of errors and so on. If you manage to do this before the end of the day, I'll be here until tomorrow 5 a.m. or something. So anyway, we can discuss it maybe over tea or over dinner or something like that. And please try this exercise of computing the solutions with decreasingly smaller step sizes and see what happens to those solutions. And part of the reason why that exercise is important is as follows. I'll tell you the answer, what it comes out to be, is that as the step size becomes smaller and smaller, what exactly you were saying is what happens, which is every time you take so let's say I have taken a step size of size h and I reach here. I start at the same initial condition, take a step size of h over 2. I go somewhere nearby but maybe slightly different, and I take another step size of h over 2. I'll go somewhere nearby but maybe slightly different. So with step size of h over 2, I will not reach a point that is exactly the same but slightly different. Now, as soon as for a chaotic system, you introduce a small error, and even if you had exactly analytical solutions available after this time, because of this small tiny difference that introduced at the first time step itself in a way, the trajectories will diverge even for analytical solutions of this. Of course, sorry, chaotic systems do not have analytical solutions, but suppose you were a god or something like that. I don't know if gods have analytical solutions. And you could get, even then, the uncertainties will grow in time. So in a way, when talking about numerical solutions, talking of a single numerical solution or trying to approximate a single trajectory is inherently not a great idea. There are 2 ways around it. One goes by the route of what is said to be shadowing. I'm not going to talk about shadowing lemmas and so on and so forth. So shadowing is an idea that tries to get around this problem that there is simply no way of capturing a single trajectory of a differential equation, a chaotic dynamical system, with any accuracy, with any numerical method. So the shadowing ideas try to find theoretical ways to go around it, define appropriate quantities such that you can still make meaningful statements. The second way, which is related to this, is just completely get rid of talking about a single trajectory, always talk in terms of probability distributions on the trajectories of interest. So you always think of probability distributions rather than a single trajectory. And that kind of essentially is one of the motivations for saying that, look, even if you have any accurate numerical method, you try to make it more accurate, you will actually get a different trajectory. You try to make it more accurate, you will get a different trajectory, and that will keep happening. That is simply not going to go away without for a chaotic system. So in fact, one thing you should do is the same exercise which is in that notebook. Do it for a non-chaotic system. For example, let's say a harmonic oscillator or a pendulum, single pendulum, and see what happens. As h goes to 0, the errors actually go to 0 for a non-chaotic system, but not for a chaotic system. And that's where another motivation, which is that instead of studying a single trajectory, you study ensemble, a sample of trajectories that basically is a representation of a probability distribution. So that's one motivation, connecting the first part to talking about uncertainties. And the time evolution of the Lyapunov vectors, basically the vectors, the eigenvalues and eigenvectors of this matrix M, actually, they are not exactly, the limits of the eigenvalues and eigenvectors of this matrix M is what gives you the Lyapunov vectors, which is what tells you the growth or the decay of the solutions, of the uncertainties in the solutions as a function of time. And the second notebook was supposed to, not notebook, set of programs was supposed to illustrate that, but I think we simply have completely, totally, utterly run out of time. So I'll stop here. Yeah.
Has